trigonometry well, we know for when we have a right triangle, we can solve for the sides using Pythagorean theorem. So let's write that here. A squared plus b squared is equal to c squared. But there are some triangles that have a pattern to them, so if you can recognize that pattern, then it's easier to solve them and you don't need the entire formula. So those are called special right triangles. So we have two of them, a 45, 45, 90 triangle, which is 45 degrees, and 90 degrees. And let's do it over here, a 30, 60, 90 triangle, which is 30 degrees, 60 degrees, and 90 degrees. So when we have two angle measures that are equal, that means the sides are going to be equal, so we can just set this as x. And if you were solving for that, our a is x squared plus our b is x squared is equal to c squared. So if we were solving for c, which is the hypotenuse, well, x squared plus x squared is 2x squared is equal to c squared. If you took the square root of 2x squared, that's equal to c, but you have that x squared inside, so you can take that out, and that gives you x square root of 2 is equal to c. And that will be true for all triangles. If you, whatever you plug in for x, you can solve for that. So all you need to have is the knowledge that when it's a 45, 45, 90 triangle, then those two sides are equal, and the hypotenuse is equal to one of those sides times the square root of 2. So that one is just simple Pythagorean theorem, but now you can solve it using only one side rather than having to have two different sides in order to solve for a missing side. So for a 30, 60, 90 triangle, it's kind of similar, but it's a little bit more complicated. So when you have, oh, that's awful. When you have an equilateral triangle, so each vertice is 60 degrees, 60 degrees, 60 degrees. But in order to get a 30, 60, 90 triangle, I'm switching to a different color, we can split it straight down the middle. You have this 90 degrees in the center here. Now this is 30 degrees. So if you set each side of the triangle equal to 2, then that means each length of the short leg is equal to 1. So if you split that, then you get your 30, 60, 90 triangle. And you have 1 here and 2 here. So if you plug that into your Pythagorean theorem, a squared plus b squared is equal to c squared. Our a is 1. We don't know what b is. And our c is 2 squared. So our b squared is equal to 2 squared minus 1 squared. Our b squared, 2 squared is 4. 1 squared is 1. So our b squared is equal to 3. And when we take the square root of that, then that's the square root of 3. So when you solve for this last leg, it's the square root of 3. But again, similar triangles, so you can plug in any number and multiply by these values in order to get the same angles and keep them. So you have 2x, 1x, and x square root of 3. So if we switch back to black, our special right triangle here is x square root of 3, and 2x. So it saves you a little bit of time with calculating them, and especially when you get into more math involving these special right triangles and with the unit circle, it's helpful to know these values. Again, our 45, 45, 90 triangle means that our legs are x, and our hypotenuse is x times the square root of 2. And for a 30, 60, 90 triangle, our leg that corresponds with the 30 degrees is x. Our leg that corresponds with the 60 degrees is x times the square root of 3. And our hypotenuse is 2x, which corresponds with the 90 degrees. All right, so that's one thing that you need to know for similar triangles. Your ratios are always going to be the same with these special right triangles. So let's go into something else with right triangle trigonometry. Let's get rid of these. All you need are these triangles? Okay, so hopefully you've committed them to memory as best as you can, but let's do a couple of problems with them. So if you had, actually let's get rid of them. Let's see how much you guys remember. We erase all of that. Okay, so if you have a triangle that looks like this, 90 degrees, and then let's make this 30 degrees. A, B, C. Our BC value is 6, and our AB value is x. So find x. Well, if you have a 30 degrees here and a 90 degrees, then you know that this has to be, let's do this in another color, let's do it in galaxy. Then you know that this has to be 60 degrees. So if you have 60 degrees, then you know this is a special right triangle. That's 30, 60, 90. 30, 60, 90 means you have x here. Our height is x root 3, and our hypotenuse is 2x. Luckily, we have our x. Our x is 6. Actually, what if we, okay, let's make this find y, just so then you're not confused. Find y, and then this is y, or whatever, it's the same color. So if our x is 6, then our 2x, let's do this, x is 6, then our 2x is 12. 2x is equal to the y, so this here is 12. So y is equal to 12. All right, if you have one that's like this, all right, let's do like this. A, B, C, this is our 90 degrees. Let's say this is 45 degrees. Our AB is X again, and our BC is 3. Actually, our AB is Y again, and our BC is 3. So find, that is not the right word. Find Y. Well, we know that if this is 45 degrees, then our A is also 45 degrees, and that's a special right triangle, given that that's what we're learning right now. So 45, 45, 90 triangle. And in order to solve for that, we know that this, let's switch back to galaxy, this corresponds with our X, which means this is also X, it's also 3. And our Y would have to correspond with x square root of 2. Well, if we know x is equal to 3, x square root of 2 is equal to 3 square root of 2. So this is your answer, but you can also multiply that out. So our answer is 3 square root of 2, or 4.24 is what you would get if you multiplied that out. So that's your answer there. All right, so what about trig ratios? You already know these special right triangles, but what about like using sine and cosine? Well, you hopefully already know what sine and cosine are, but if not, here's a quick review. Sine and cosine, if you used our SOHCAHTOA mnemonic device. SOHCAHTOA mnemonic device, then you know that sine of any angle, sine theta, is equal to opposite over hypotenuse. That's your opposite here and your hypotenuse there. Let's write that out actually. That's your opposite over your hypotenuse. Hypotenuse. Your cosine of any angle is adjacent over hypotenuse. Over hypotenuse. And your tangent theta is opposite over over adjacent. But tan is special because that would be the same thing as sine over cosine. Because if you have opposite over h and then you divide that by adjacent over h, you know that if the denominators of both are the same, then they cancel out and you end up with opposite over adjacent. So that's how you get sine over cosine. But those are the main three that you know, but there are three others. So there are 6 trigonometric ratios. You already know 3 of them. You might already know the other ones, but they're basically the reciprocals of these, of the ones that you have. So the reciprocal of sine, 1 over sine theta, is equal to hypotenuse over opposite. And the formal name for that, what that trig ratio is called, is cosecant theta, or written as CSC theta. Our inverse cosine theta is, I won't write it out anymore, adjacent, hopefully you can tell what the letters mean, adjacent over hypotenuse. Our cosine is adjacent over hypotenuse. Our inverse cosine would be hypotenuse over adjacent. So the formal name for that is secant theta, or written as SEC theta. And again, that's hypotenuse over adjacent. So a good way to remember these is that sine, starting with an S, corresponds with cosecant, starting with a C. So they're flipped. And cosine is corresponding with secant, which starts with an S. Again, that's inverse. Our tangent, 1 over tangent theta, is equal to adjacent over opposite. Formal name for that is cotangent. You don't really need any special tricks to remember this because it's in the name. Cotangent theta, or you can write it as COT theta, and that's adjacent over opposite. So there are 6 trig ratios. There isn't a mnemonic device to remember cosecant, secant, and cotangent, but if you remember which ones they correspond with, it gets pretty easy. And obviously, the more you use them, the easier they are to remember. So let's do a practice problem with one of the trig ratios. Let's do one with one of the new trig ratios. Let's get rid of everything here. There we go. All right, let's do, that's triangle like this. I wish I had like a ruler that would work, but don't care that much. A, B, C. So let's solve for C. Let's say our B is 17, our C is 15, and our A is 8. So that's the same thing as BC is 8, AC is 17, AB is 15. So let's solve for, find cosecant of C. So if we need to solve for cosecant of C, what's cosecant? Cosecant theta, sorry. If you're writing notes to yourself, you can obviously just write CSC and leave it at that, but considering that it's like you have to have an angle with it, let's write it with theta. So cosecant of any angle is the same thing as 1 over the sine of any angle. Now sine is equal to opposite over hypotenuse, so cosecant is equal to hypotenuse over opposite. So if we're looking at, let's go back to galaxy, I like that one. If you're looking at C, then hypotenuse is 17. Hypotenuse is equal to 17. And our opposite is equal to 15. So our answer there is 17 over 15. Now you can also find sine and invert it. So sine is opposite hypotenuse. Opposite is 15, hypotenuse is 17. If you want to just invert that and do the reciprocal of that, you obviously get the same answer because they correspond. It depends on what's easier for you and what you are most comfortable with doing. But that's it. These can really help when you're doing the unit circle or you're finding any triangle, really. When you have all of these ratios in hand, you never really struggle as much with finding them. But that's it. Hope that helped.